Okay. I need someone to read starting at the top. Thanks for volunteering, Gene. Share your hand up. Okay, when it's quiet. Just be patient. When it's quiet, you can start.
The cue ball collides with the stationary pool ball. The cue ball is initially moving to the right with the momentum shown below. After the two balls travel to the direction shown, all balls have the same mass, like 25 kilograms. Use this information to do the activity shown below, and note the vectors below only show direction, and their length is not meant to correspond to any vector magnitude.
Okay. Now, I gotta step back. Before we do this, are you folks realizing that a collision happened here?
Yes.
Yes.
So this one here is before a collision,
Yes.
and this is what happens after the collision, right? Before the collision, only one object is moving. It hits the other ball is hit by the cue ball, right? But the other ball that's here was not moving before the collision. Cool? And then after the collision, the cue ball is moving like this, and the other ball is moving like that. Is everybody good?
Yes.
And to go back for homies that are stuck, like lost, let me, I'll put this, right now this is only on the CP site, but I'll put this on your site too, because it's good for everybody. There's a simulation that'll help you figure out some things. I'm just going to open it up. No. I'm going to click on velocity, click on momentum. I'm going to click on momenta diagram, okay? Because some of you have no clue what momentum is because you didn't watch the video yet, right? Okay? So here's what you can do. First, I'm going to move these objects apart. This is different than the example that you just saw. In this example, two objects moving towards each other, right? I could press play. Kind of cute. Thank you. Restart. Play. Restart. Is everybody good? So do play with this for the weekend. It'll help you a lot. Now, I can use my, these yellow vectors are momentum. That's why it's called a momenta diagram, okay? Okay, we'll get there. That's a great question. What does momentum mean? Observe. The green arrow, if I uncheck it and check it, notice that the green arrow is what?
Velocity.
Good. Okay. The yellow arrows are what?
Momentum.
Okay. Everybody good so far?
Yes.
Okay. So observe. If I change my velocity vector, does my momentum vector change?
Yes.
So obviously momentum depends on,
Velocity.
but is momentum velocity?
No.
There's a trick though. I can make my momentum velocity. Are they what? Yes. Look at it. As the momentum, as the velocity goes up, does momentum go up the same, proportionally? So notice if I make the mass exactly 1 kilogram, watch what happens to the momentum compared to the velocity vectors. What do you see? You guys cool?
Yes.
All right. If I make my mass half kilogram, what's going to happen?
It's half. So velocity.
What's half of what?
Scales velocity.
So mass scales velocity to give you momentum. Isn't that cool? So momentum is what? Are they vectors?
Yes.
No. Which one is vector?
Okay.
So the definition for momentum, and if you watch the video, you already know this. Momentum is mass times velocity, and this is a scalar. Oh, what if we use m for momentum? I don't know. Maybe there's a Latin word that means momentum that starts with a P. I don't know. I should probably figure it out. That's my guess. So everybody good here?
Yes.
Is momentum a vector?
Yes.
Okay. So, and we have this as yellow vectors here. Okay, now, this question is only for those people who didn't watch the video. Those that watched the video, please answer the question in your head. You already know it. Okay? If I add these two momentums, this is before the collision, right? If I add the two momentums, I have to follow the rules of adding vectors. Is that true? Okay? So when I follow the rules of adding vectors, I place the vectors head to tail. Yeah? And I get this little red dude. The red dude says tote on it. What do you think the red dude is? Total, right? Tot, total. So the red is the yellow's added. And I can add it in any order, right? I can go this one, then this one. And I'm getting the same vector result, right? So the red, cute little red vector is the yellow one's added. Now, those that watched the video, those that didn't, only the ones that didn't get to speak, but those that watched the video, please think about it. Notice the red vector before and after the collision. Notice the red vector. Go. Did you see it? Wow. Did anything happen to the red vector? Okay, look carefully. Oh, maybe I just didn't make the mass big enough. Hey, nothing interesting happened to the red vector. Oh, maybe it's because this type of collision is called elastic and things are bouncing. Maybe if I make them stick, that's inelastic. Let's see what happens then. Doink. So, as a general rule, what could you say?
The sum of the momentum from like 1 and 2 is good. But your total momentum doesn't change.
Please say it again, see if anyone nods.
The total momentum will never change, regardless of the collision.
Now, there's a few assumptions here that you may not be aware of. When you say will never change, there are conditions that change momentum. But in this specific simulation, what do you think the assumption is? These objects are hitting each other? Is there anything else hitting them? Are there any external forces? You guys dig the assumption?
Yes.
That's key. Well, the forces acting on this guy consist of that guy. It's just the length of the arrows. Why don't I just take them off for a minute? Whoops. Haha. If I take them off, when they hit, who hits who?
It's to hit each other.
Is anything else hitting them?
No.
So there's your fundamental assumption with momentum. And we use this to figure out, like, we shoot little pieces of atoms at each other and measure what we get from the collision. We do all kinds of things in real life. We slam cars together and look at how safe they are. We look at the skid marks of a car, figure out how fast it was going after the accident, and then we figure out its speed using rules of momentum. We figure out what the speed was before, and if they were, you could actually get in a car accident and from the skid marks get a speeding ticket or even a reckless driving ticket, or even lose the court case because you were speeding after the fact and no one actually saw you speeding directly. You get what I'm saying? Momentum's a powerful concept. And the fundamental idea you just said was what? Before and after the collision, what didn't change? So we didn't say, notice we didn't say the momentum of object 1, because that changed. Notice we didn't say the momentum of object 2. That changed. But the sum of these two arrows, see how I place them head to tail and I get the red one? Did the sum change? You guys dig. Okay? So there's before the collision. I need to move them around sometimes, but always the sum of whatever things are moving, the sum of their momentums has to give you some number, and that can't change. Cool? And again, the fundamental assumption is what? Louder. That's about what I heard. What? Yeah, that's key. All right. So now I think you're ready for this. Now we have a collision. We know the momentum before was what?
2 kilograms per meter a second.
Okay. The momentum after is what?
2 kilograms a second.
So I should have said total momentum before, total momentum after, right?
The total is
Is this amount going to change?
No.
Now, in the end, you have two things moving.
almost total.
So how is this going to look? These are the two things moving. To figure out the total momentum, what do we have to do here?
Add them up.
So these two vectors have to add to what? Not the number 2.
2 kilograms a second.
Not the number 2. It's the vector that has a magnitude of 2. You guys good?
Yes.
So let's see how that'll play out. This question's asking, what's the momentum of the cue ball?
Wait,
30 degrees to the
Okay, that's this. This is done already. What's the momentum of the other ball after the collision? That's done already. What's the direction of the total momentum of the system at any moment? What's the direction? Which way?
To the right.
So just that way. You guys good? And you see how we got that? Because that was the momentum before, and that total momentum can't change. You guys good?
wait, so okay, when the initial or the cue ball is going in that one direction, it is going horizontally at 2 kilograms or what is it?
Just say that's the momentum. The momentum of 2.
Momentum 2, and it's going horizontally. So even after it hits the other ball, the momentum is still 2.
What momentum?
The cue balls.
Not just the cue ball.
The total momentum.
That's where you have to be careful.
Wait, what do you mean, like total of each or total together?
That's where we have to be careful.
The total.
What are we talking about? Could you clear it up?
Total of each.
So you have to do what with these vectors?
Add them up.
Yeah, so then.
So
and
these
then they're equal to-
these vectors, we don't know the length, right?
Yeah, so then-
It says we don't know the length. So I'm just going to draw it like there. I'm going to say it's some length that I don't know. And I'm going to say this vector, right, plus this vector has to equal what?
2 kilograms.
And this vector is facing that way. So I'm going to draw it that way. And I'm going to label it 2 kg meter per second. That vector has to be 2. You know what? I'll just make life simpler and just label the number. If that vector is 2, and these have to add to it, can I now adjust the lengths maybe like that? Do you folks see how I'm doing it?
Yes.
And I suppose this is probably a right triangle because this one was given as 30. That makes that one 60, which was given. Is that right? Because that rule about if I do some reference lines here, we were given what? We were given, oh, you need a horizontal there. We were given this as 60 there. So that must be 60. Are you guys cool? Right on. What's the length of this side?
Which side?
what?
Good. What's the length of this side?
3.
Okay. I decided to make a really hard one here. I thought that was funny. This is hard. It's a 1, 2, 2. Okay. Not that funny. So what can you find if I also say that everything has a mass of 1/4 of a kilogram? What can you now find? How?
From the, well, you can find initial velocity too.
Okay.
Because the
What's the initial velocity of this dude?
8 meters.
How are you getting that?
I divided by 0.2.
You guys don't want to miss this logic. This would be very important. Say it again.
I divided by kilograms to get its initial velocity.
Okay, so how did you know divide by the mass?
To get rid of the units. So I'm looking for velocity.
Okay. I like it. I like it. So your claim is that velocity is momentum divided by mass.
Yes. Right.
Is that right? Is momentum equal to mass times velocity?
Yeah.
Is this relationship true as well? So you're right. You use the units to figure it out. You got 2 kg meter per second divided by the mass of quarter of a kilogram, and you're saying it was given right here. Circle it there. So you got a velocity of 8 meters per second in the beginning. Can you play the same game with this momentum, that momentum, and that momentum, and figure out how fast everything's moving?
Yes, you divide by a
So-
quarter.
So how fast is, which one's this? This is the cue ball. So cue ball, how fast is it moving? You don't have to go through the whole setup now. Just tell me how fast it's moving. Show me you understand it.
6 meters a second.
It doesn't have to be an exact number. You can use radical 3.
Oh.
What's it going to be?
Radical 3 over 0.25.
Radical 3 over 0.25. Isn't that going to be just the same as multiplying by 4?
4 radical 3.
So 4 radical 3. That's a very precise answer, and that's better than actually a decimal. So it's going to be that meters per second. And what about the other? What's its velocity going to be?
4.
Also, all right, velocity other 4. What do you folks think? You guys see it?
What's the other velocity?
Well, if the momentum is 1,
Oh, sorry. I didn't know.
that's okay.
That's
Other ball is here. So have you now figured out the momentum of everything before and after the collision, the velocity of everything before and after the collision, and you already knew the mass of everything before and after the collision? You guys good? So we've done all of this. What do we know about the total momentum of the system before and after the collision? That should be really easy. Yell it out.
Same.
Okay, same. Using your answer to question 4, create an appropriate vector triangle. Okay, didn't we just do that? So that's there. And then I'll go to the next page. Redraw with and insert appropriate numbers. Did we do that?
Yeah.
Okay. Did we? What quantities did we not know from our vector triangle? We only had one momentum. Remember that?
You didn't have either the
We didn't have momentum cue ball. We didn't have momentum
other ball.
other.
You had the angles.
We had the angles. What else didn't we have?
Oh.
We didn't have the velocity of the cue before, right? We didn't have the velocity of the cue after. Did we find all of this? We didn't have the velocity of the other after. Did we find all of it? And we did. This was done. Cool? Everybody good? So, oh, there was one more question. I'm sorry. My favorite question on here. What did we do in general? And I'm going to help you with the first step. So, the question is make a general procedure that's always going to work for solving any momentum problem. This procedure must be general. You good? So, first thing that was given to you is diagram of before collision, after collision. So, if I redraw it, you were given this. You had a cue ball going this way. You had other ball, I'll just make it an 8 ball, standing still. So its momentum is 0. Did you need to include this momentum in the total? Try that again. Did you need to include the 8 ball's momentum?
No,
Because it wasn't even, its velocity is 0, so its momentum 0. So adding it does nothing. Cool? After the collision, Which way was cue ball going?
32.
Okay, so you had this, and you had this, right? And this is other, or 8 ball, let's say. And this is cue.
What about the momentum of the 8 ball after?
This 8 ball.
Yeah, that big ball.
We found the momentum of the other ball. We called it other ball. Is everybody good? So that was first step. I don't know if you were aware of it. What would be next in a general procedure? What did we do to solve the problem? Create, okay, I'm going to call it a vector diagram. So I'm going to write create vector diagram. And do you need to keep track of, think about all the possibilities here. Do you necessarily have one object hitting another object? So one object's momentum being equal to 2 objects' momentum added. Is that always going to be the case? You could have, and you could have 2 objects moving in the beginning and actually sticking together. So 2 objects' momentum in the beginning could be equal to 1 object's momentum in the end. Do you understand what I'm saying? What's the fundamental principle behind your vector diagram? What has to be true? What law do you have to follow? That's okay. What do you know about momentum before and after a collision?
Always the same.
So this must follow, this vector diagram must follow that. So I'm going to call it law of conservation of momentum.
So vectors before collisions and vectors after.
Yeah. Now do you understand why we have a before and after?
Yeah.
I mean, this is P total before equals P total after. Is everybody good? And then what did you do next, please? What did you do after that? After your vector diagram, it was pretty much solved, but what did you do last? Okay. Who's first? You go first, and then she'll go. Okay. You used, yeah, that was further down. That was like the last step. You use this relationship, right? And that's just definition of momentum. Before that, could I say in general that you use what you know to find what you don't know?
Yeah.
I mean, that's always going to be true. So you just find everything you don't know from what you know in any problem? Well, it's not always easy to figure out what you know and figure out what you know from what you know, but that's essentially what we're always doing. Your question was?
Well, you still explain this, but
Okay.
I don't understand like how the total momentum is distributed. Like what's the okay, I understand that the momentum is first like concentrated in the cue ball once it's moving, but then the ball is still. So once they collide, does the momentum get distributed to both of them, or is it still only the cue ball?
I don't have a good answer. All we know, and the fundamental principle in solving these problems, you're not so much worried about the momentum of the individual objects. You're worried about what? And you just have to...
I don't understand if it's in both objects or not. It is, right?
If an object is moving, will it have momentum? What 2 things has to happen for an object to have momentum? So you need to account for any object that's got mass and moving.
So it's both.
Does that help?
Yeah.
Would you guys like to see an example?
Yes.
Okay, and I'll just take this straight out of your worksheet, okay? All right. So, in the last years of my dad's life, right, he was sort of, he was blind. He wasn't totally blind. He could see, like, faces from certain distances. It's okay. He had a really good life. but and I played pool with him a lot because he built a little pool table and he figured it was something he could do that wasn't extremely athletic. You know, it was pretty ingenious. And I lost every game against him because I couldn't do a draw shot. Do you know what a draw shot is?
Is that the
first one?
Okay, I'll show you.
I can
I'll show
only
you.
do jump shot.
Let's say every ball, this is the cue ball, so it doesn't have a little Q. I just wrote Q because it was a white ball, okay?
Yeah.
And Q is really CUE, okay? So let's say this is the cue ball, and if you hit the cue ball below center, it will have spin on it, which we're not taking into account, okay? That's why this problem is not physically correct, because we're ignoring things that are important like the spin, okay? But it'll still work out. Our momentum rules will still work out, and we'll be able to solve stuff. It's cool, okay? So if you hit the ball just right, it'll come back to you. Instead of, in my case, what it ended up doing is both balls. See, to win the game, the 8 ball has to go in, right? Okay, in my case, I'd hit it, and both would go in, and then I'd lose, like every time, okay? And don't ever bet on pool. It's illegal and wrong and messed up.
What if it's with friends?
But whatever you bet is now you lost. But I wouldn't bet.
Yeah.
So what you want then is the cue ball to come back to you. It's a really cool shot because, and it's not even that hard. I'll post a video on how to do it just because it's interesting to me. And I think it's actually pretty easy. And to have the ball come back makes it possible to make a lot of shots where you make a shot, the ball comes back to you, and you can make the next shot, ball comes back to you. You know what I mean? You can like go on a run with this. Anyway, that's a draw shot. And I'll give you the mass of everything. So this is my before and after. Is everybody good? So that's before, that's after. So, make the mass 0.16 kilograms. Make the mass of everything, because they're all the same mass, I believe, in pool. Is everybody good so far? Cool bananas? They might be slightly different. I'm not gonna worry about it. Okay, I'll make some. I'll make this like. Let's see. I'm taking this off your worksheet, by the way. This is number 9. You don't have this worksheet. But you will. 0.35. So I'll make this velocity 0.35 meters a second. I'll make this 0.07 meters per second. Notice that's small. And I'll make this like, oh boy, it would be so nice if we could find how fast the 8 ball went in as you win the game. Okay? You could relive the glory and figure out how fast the ball went in the pocket. Okay? I didn't mean to do that. Thank you. You're cool. This is actually velocity, and this is left. That's to the left. We know this velocity is to the right. We know this velocity here is 0. So we know its momentum is 0. So we don't care about it. And we know this is a momentum to the velocity is to the right, so the momentum's to the right. Is everybody good so far? Let's try to do our vector diagram. Which way do I draw the arrow here? To the right? Okay. So it's 0.35 scaled by 0.16, right? So I'll draw an arrow to the right. Please tell me what the value is. So I don't have a calculator handy. I want 0.35 times 0.16. I'll wait for you to do that. 0.056. Thank you. Is everybody good? Everybody sees that we got that? Everybody sees why we did that. We're scaling our velocity by our mass, right? Rafi, you good? Okay. Okay, I'm going to use a different color now. This guy's going this way. This guy's going that way, right? What's got to be true about the red vector and the 2 blue vectors? What do you mean they have to be equal?
Equal to
They
12.
have to
The 2 blue vectors have to equal to the red vector.
So the two blue vectors must add head to tail to make our red vector. So which one of these must be a lot longer?
The right one.
So that's the logic that you need to go through.
Oh.
It's hard,
Yeah, it's hard.
but it's cool. It really is cool. So I'll just make a really long one, and I'll say I don't know what its momentum is. I don't know this long one at all, but I do know that that long one plus this blue one should add together. So I've placed them head to tail, right? You see how I placed them head to tail? We'll get there in a minute. Hang in there. So those two must add to equal this one. And I know what this one is. This one appears to be a little short, right? Or what I'll do is I'll shorten this guy. And now they'll be good. Do you see what I did? Do we know the length of this one already?
Yes.
What is it?
0.056.
About everybody.
1.056.
There's got to be something else we know here.
The small.
The small one. Okay. What is the small one going to equal?
0.011.
So you're just finding its, how did you do that? You did 0.16 times 0.07. Is that right?
Yeah.
Okay. And you got what?
0.011.
0.011. All right. Now, does anyone see how you're going to find the magnitude? So for now, you can forget about the directions. You already have the direction everything's moving. You can totally forget directions. Does anyone see how you're going to figure out the length of this guy? The simple way. Just add them together. What do you get? What's that one got to be?
0.067. 0.166.
What?
0.067.
0.067. Okay. Now does everyone see how you're going to find the velocity of the 8 ball going in the pocket when you win?
Divided by 0.6.
Is it what?
Mister, do you have a question?
Hold on. Does everyone go? You go first.
If all the masses are the same, can't we just ignore them? Just look at velocity alone?
Yeah.
Because if you divide by it, you could leave it on.
Your numbers will be wrong.
Not in this one. Either way, the answer 0.42. I checked on the calculator.
I just had an insight. If you used MV for everything instead of a number, what you would find then is the M would cancel out,
Yeah. Because that only works if they're all the same.
which is rare. But you can figure cool things out that way. You're right. Cool. How in what are you going to do here to find that? Everything. Why? What's your logic? Okay. So you're basing it on this. Momentum is mass times velocity. And you're finding velocity. So you're just taking your momentum and you're dividing by mass. Everybody's cool, right? These aren't that bad. This is actually towards the end of your worksheet, so it's not an easy problem. The way we're doing it with the vectors is totally unique. Haven't done it this way ever in my life, and I really like it. The previous way we used to do it is with an equation people memorized and didn't understand. This is totally understandable, requires almost no memorization, so to me it's really beautiful. And it makes sense. Cool? I think it gives you, I really think it gives you a better grasp of the physics, of the concepts. So you're doing, what? You're doing 0.067 over 0.16, is that right? Or am I messing this up? And you got what?
You get 0.41375.
Okay, so 0.42 is fine by me. And this is the, and if I say this is the, how fast 8 ball moves into pocket. And I'll say to the right. This is to the right, right? Is everybody good? Not too bad, right? Questions before I move on? Yeah. Help her out. What is momentum exactly? It's a great question. What is it? Go back here. If this is why playing with this will really help you. If you just play around with this, yeah, I'm putting it right after you leave today. I'll put a link to it. I'll put an image of it that you can click on, and below that I'll put a link to the website where I got it. Okay? If I just play around with this, just look at object 1, forget object 2. You with me? Forget object 2. Just object 1. What's happening when I change the mass? What's happening to the momentum arrow? So, does momentum depend on mass? And if I change my velocity arrow, which is the green arrow, I'm just dragging it. Does that change my momentum? So clearly, momentum is what times what? And
kilograms, meters a second.
and that's why the units are bizarre, kilograms, meters per second. There's no special unit for momentum. I prefer thinking of it as it's your velocity vector made bigger or smaller, in other words, scaled by your mass. That's all it is. When your mass is 1 kilogram, your velocity vector and your momentum vector are what? Yeah, they're identical. That, for me, that's a really nice way of thinking about it. When your mass is above 1, your momentum vector is simply longer than your velocity vector, but in the same direction. When your mass is less than 1, your momentum vector is less than your velocity vector. So it's your velocity vector scaled by whatever your mass is. Does that make sense? That's, to me, that's the most beautiful way to conceptualize it.
Oh, you ignore it.
Friction would be an external force that would make the total momentum before not equal to the total momentum after our collision. So that's an example of something we are ignoring. Cool? I do have one more thing to show you. Let me go to your website real quick. Let's see here. All right, there we go. And if I go to momentum, okay, this is actually really cool. I'm excited for you guys to figure this out. Please look up. Consider number 1. To make it easy, pretend this is a rectangle, so it's easier to find the area. You need to consider the units. What's the area under this graph? It's a force time graph.
Momentum.
It's not momentum, but you're very close.
It's kilograms.
Yeah. What's the area under this graph represent in physics? You guys figure out the units yet?
Kilograms, meters a second.
When you multiply newtons times seconds, this is the same as kg meter per second squared times second, which is kg meter per second. I agree with you, the units match momentum, but I'm telling you it's not momentum. You should probably reflect on the areas under graphs throughout the year, what they have meant. All year, would you guys agree that the area under our graphs have always been a change in something?
Yeah.
And the units match momentum?
I read it. That's right. I just
So
read the graph.
this area is the change in what?
Change. Momentum.
You guys cool?
Yeah.
And you can see when a change, is this an external force acting on your system? Could this be an external force acting on a system?
Yes.
If this were a rectangle, it would simply be newtons times seconds, right? And the fact that it's a curved shape doesn't really matter. Cool? So,
That's what a Newton equals.
this is the same as that. If you forget what a newton is, which has happened to people all day today, I've seen that, just write second law out and say, well, a newton must be a kilogram times a meter per second squared. Bam.
That's an easy way to think about it.
Go back to second law. and figure out what a Newton is that way. You guys good? Because second law is something you should just know.
Well, I know that, but I don't know the after that.
From what to what? This to that? How do you measure force? I'm doing, the black is the units for my equation, and I know they have to work out. Good? You guys cool? This is a million times better than memorizing. Just going back to the basic stuff and figuring it out. You'll grow a lot that way. You guys cool? Do you want to finish this one or what? We'll totally make it. The rest is easy. That was the beautiful part that usually opens a floodgate for the rest of the worksheet. Like, is your answer for number 1 an absolute or a change? It's a change. Any area under a graph is usually a change in something, right? Could you estimate the area under the graph? What would I want you to do here? How would you do that?
From 3 to 15, then the height makes around a triangle.
Sure. Okay, so you could make this a triangle. That's a great idea. I like it. What else?
2 rectangles with a triangle on top of it.
Okay, this maybe a trapezoid. And maybe a rectangle.
Make it too ridiculous.
You'll do it. I'm cool with however you do it.
But you don't.
You what?
No, you need it.
What's that?
And that won't work because you don't have the function. Yeah.
You guys are thinking calculus, huh?
Yeah.
This is the basis for calculus. This is the basis for every integral.
No.
So do it the old school way with a lot of error and make up some basic shapes, and it's not a big deal.
It's not a lot of it.
Just go back to the foundation of integral calculus for fun. Cool? And then hey, after you do it, hello. After you do this, you would want to sort of consider what it is you found, and I want to give you a hint what it is you found. Okay? You said this was the change in momentum, right? Okay? Change. Well, in the examples I gave you, there was no change in momentum before or after the collision because there were no external forces. But when there is an external force,
But it's accelerating.
you have changes in momentum. So let me, okay, a change in, if momentum is mv, would you agree that the mass isn't going to change even if the object's momentum changes? Go ahead. Huh? Yeah. An object's mass isn't likely to change. It could, but more likely, I would say it's a change in velocity that leads to a change in momentum. And the area of this graph, calculus or any other way, is much simpler if you have a constant force, and this is a rectangle. Are you guys with me?
Yes.
So in the simpler case, where you have a constant force that's external applied to a system, I don't even need the delta t there. I could just write F times t, right? And this side of the equation is called change in momentum. This side of the equation, in physics, we call it impulse. An impulse will always equal your change in momentum. We don't use this relationship hardly as often as the fundamental law of conservation of momentum. That you use all the time. This is a kind of a little side note that allows you to do interesting things. And we'll save that for another day. Make sense? You guys gonna watch the videos? Your official homework